from the preview activity, it gave us this equation, and we did the area under the curve on this one, and I think it came up to be, I forget, 24, something like that. We'll figure it out here. So we want to find the antiderivative of this, but we're going to write this in an integral notation, and they talk about the definite integral. I'm going to talk about that in a sec, but it looks like this. It says add up the sum of everything from 1 to 4 under the curve x squared plus 1 with little tiny changes in the x, and infinitely narrow columns. So use that as the height, and that is the width of the column. Add them up from 1 to 4. And the other way to do this is to do, instead of using that app, is to do the antiderivative of x squared plus 1. And if you remember right, the antiderivative of x squared, what you would take the derivative of to get x squared would be, it would have to have x to the third, but the derivative of x to the third would be 3x squared, because you take 3 down and reduce that by 1. So we have to do 1/3 x cubed, so that 3 times 1/3 makes 1, x to the 1 less than 3, 2. That's the antiderivative of that, and then we do the antiderivative of 1, which is just x, and then we're going to evaluate that from 1 to 4. So this vertical line at the end says, figure out this expression's value on the interval from 1 to 4, which means, like, if this was a velocity equation, then the area under it would be the distance. Well, if this would be the distance, because the derivative of it is the velocity, so this will give us the distance. So we're going to find the distance it's at 4, and then we're going to find the distance at 1, and we're going to subtract it to find the change in the distance, which is what the area represents. So we're going to put 4 into here, the ending, beginning, end, put the end in here and find out where we're at. So 4 to the third is 64 divided by 3, plus 4. So that's where it's at after 4 seconds, or wherever. That's what the value of the antiderivative is at 4. Minus the antiderivative at 1. So I'm going to put 1 in there, and that'll be 1/3 times 1, which is 1/3, and plus 1. So I have, let's see, that's 21 and 1/3, plus 4 is 25 and 1/3, minus 1 and 1/3, which turns out to be 24. That's the exact area under that. Now another other notation for this. We're finding the integral from 1 to 4 of f of x dx, which is capital, the antiderivative, the capital F of x. That's the antiderivative of lowercase f of x, evaluated from 1 to 4, which means we find f of 4, capital, the antiderivative of 4, minus the antiderivative of 1, which is what we found the antiderivative, and this is the f of 4 plugged into it, minus capital, the antiderivative 1 at 1, which is that. So that's how we can get the exact value. Okay? So then, the book says what we're supposed to surmise by looking at that app, that if you make more and more rectangles with the left side on the curve, that left Riemann sum will get closer and closer to the correct value of the area. Same as the right hand one will do the get closer. So these both become closer and closer to each other, And the midpoint, which is already the better, seems to be better most of the time for these than these two, it also gets closer and closer to the right value. And it's what happens to this summation. When we add up the heights at all the different widths, at all the different places from 1 to n, and keep making n get bigger and bigger, so we add up more and more narrower, smaller rectangles, narrower rectangles, but more of them, we'll get a better answer. And they turn out to be, that turns out to be what the exact area is if we do an infinite number of them. And so this is called the definite integral. It's called a definite integral is because we're finding the area between a definite A side to a definite B side, the area under the curve from A to a definite beginning and end. That's why it's called a definite. This is called an integral. Integral is a sum of a whole bunch of rectangles, and it's on the interval from A to B because we start at A and end at B, and it's written this way. The width of them, if we keep doing more and more, the width becomes narrower and narrower and narrower until it becomes an infinitely narrow one, dx. It's a tiny change in x. That's why that's there. Tiny change in x times the height of the function at the different places is what's going on here. The height times the width from A to B of all the rectangles. S, that elongated S, meaning sum, add them up. And it goes through and explains what the delta x is. We've talked about that. And that we have to start at the beginning place and then jump a delta x over each time for get these different xi's, which we've done already before. And each xi's between those things. And I goes from 1 to n. This symbol is called the integral sign. We're going from A to B. Those are called the limits of integration. And the function inside, the thing we're taking the integral of, the one we find the antiderivative of, is called the integrand. And if we figure out what this is, that's called evaluating the definite integral. We're finding the area under the curve from A to B. We're evaluating the definite integral. Okay, so that's trying to get you to understand what this symbol is all about. So here's a curve that they made up. These are different colors, but in the black and the gray and white, it doesn't show, but it says if from A to B, from A to B, from A to B, we find an area, well, that's that area 1. And from B to C, we'll find an area, and that area will be negative. Just a sec, I'll be with you in a sec. And then if we find from C to D, that area will be positive. And if we find the area from A to D, it will find that positive area. It will make that area automatically negative, and to make that area positive, and it'll find the total area here, total with that being a negative amount, so it'll be A minus A1 minus A2 plus A3, the total area. Okay? Now, what else did we do? Okay, so then if we look at this one, we already figured out that this was 3 high, 9 high, the average from on the app. We figured out this was average of 6 high, 3 wide. This has an area of 18, which they said here. And you could do it with the antiderivative too. So they go through get the average area and go through that, but we could do the antiderivative. The antiderivative of 2x would be x squared. The antiderivative of 1 is x. So this would be capital F of x. And if we wanted to find the area, we would do f at the end place, which is 4, minus f at the beginning place, which is 1. And that comes out to be 4 squared 16 plus 4 is 20, minus 1 in here is 1 plus 1 is 2. 20 minus 2 is 18, the area. And it looks like this when you write it as an integral. Okay? And then in class we said, well, can we do this one? So the integral of 3x would be, so it has to be x squared, because when you take the derivative, it goes down to 1, 2 to 1. And it has to be 3 over 2, because the 2 comes down times, so it has to cancel 2 to become 3. And we'd evaluate that from 0 to 1, which is, if you put 1 in there, you get 3 halves, minus you put 0 in there, you get 0, which is 3 halves. Then they said, look at the graph of this. 3x has a slope of 3. By 1, it's up at 3. 1 wide, 3 tall. 1 times 3 is 3, but this is half of the rectangle, so it's 3 halves. 2 minus 2x. Let's look at the graph first. 2 minus 2x, so it has a y-intercept of 2, minus 2, so it goes down with a slope like this. And we're supposed to go from minus 1, so if that's 2, this would be up at 4, at minus 1. And then if it's going down by 2, and this is 1, 2, 3, 4, it's got to go down 2, 4, 6. So it's down here at negative 6. So the area of this triangle is negative 6 times 3, negative 18 in half is negative 9. The area of this is 2 times 4, 8 in half, 4. So 4 and negative 9, the area would be negative 5. Now, if we did the antiderivative of this, this would be 2x minus x squared. Derivative of x squared would be negative x squared would be negative 2x. Derivative of 2x would be 2. We'd have to evaluate that from minus 1 to 4. So we put 4 in here. We get 8 minus 16, which is minus 8. Subtract, and then we put negative 1 in there, and we get negative 2 minus 1, which is negative 3. Subtract a negative 3. So negative 8 plus 3 is negative 5. Now for this one, harder to do the antiderivative. They're assuming that you would recognize this equation, and I'm assuming that most of you wouldn't. So if you write y equals 1, the square root of 1 minus x squared, and you square both sides, you get y squared equals 1 minus x squared. If you add x squared, you get x squared plus y squared equals 1. In that form, I'm hoping you recognize it as a circle with radius 1. So this looks like a circle with radius 1. This would go completely around, but since it's the square root and it only has the plus, it's only the top side. And so if we're evaluating from minus 1 to 1, we have a radius of 1. The area of a full circle would be pi r squared, pi 1 squared. It would be pi for this circle, for the whole circle. And since this is only the top half, it'd be pi over 2. That's the answer to that one. And finally, they wanted you to do this one. Well, we did it once before. This is 1 by 1, but only half of it, so that's a half. This is a quarter circle, radius 1. A full circle of radius 1 is pi, so this is pi over 4. This is minus 1 half. This is 1. This minus 1. This is minus 1 half. And this is half a circle, pi over 2. And so if you add all these up, so this will cancel this. This will be 3/4 pi minus 1 1/2. And that would be the area, the integral of this. The integral from minus 3 to 4 of g of x. But you could also talk about this in pieces. This could be the integral from minus 3 to minus 2 of the area under the curve. This line would be x plus y-intercept would be 3. That would be this area, plus this one would be the integral from -2 to -1 of a circle centered at -2. Circle is 1 minus x squared, but we have to move the center to -2, so we go +2. And that's what this one would be. Plus, this would be from -1 to 0. -1 to 0, start in. This line is -x, -1 slope, going through -1. Plus, this one is y equals -x, -1, from 0 to 1. 0 to 1, stay at -1. Plus, from 1 to 2, we're doing this line, which is a positive 1x with a -2 y-intercept, plus the last one, which would be a circle again, square root of 1 minus x, but it's moved over to +3, so we have to go x minus 3 to move it to +3. And we're doing it from 2 to 4. So there's the integral notation for that whole thing. All right, I'm going to stop there, and we'll continue with presentation tomorrow.